Let's wait for a couple of minutes.
Food.
I will share the slides now. Hope the slides are visible. So, good evening, all. Welcome to week 6 tutorials of the course Pericyclic Reactions and Organic Photochemistry by Professor A. Shangaraman from IIT Madras. Myself, Anisha Suresh, PMRF TF for this course from IIT Bombay. So, in the week 6 modules, Sir have mainly discussed regarding the ene reactions, followed by an introduction to organic photochemistry and some cis-trans isomerization of alkenes. So we will be discussing some problems based on ene reactions and some problems based on Jablonski diagram in organic photochemistry and some of the problems from week 5 assignments. So now coming to the ene reaction. So what is an ene reaction? The reaction between an alkene that will bear an allylic hydrogen and an electron deficient enophile, which is a pi system. It can be either alkene, alkyne, carbonyl, imine, etc. So the reaction between alkene bearing an allylic hydrogen and an electrophile, which an electron deficient enophile, which is an alkene, alkyne, carbonyl, or imine. It is known as ene reaction. So here the reaction involves a transfer of allylic hydrogen to the electrophile with concomitant formation of the CC bond. So some spelling mistake is there that I will correct. Electron deficient pi system. and concomitant formation of the cis bond. So the reaction, it involves a six-member transition state similar to the 1,5 hydrogen shift. So this is how ene reaction is taking place. This is the ene component and this is the enophile component. So here the the enophile can abstract the hydrogen and it will shift like this, resulting in the formation of this as a final product. So the enophile can be either C double bond C, C double bond O, C double bond N, C double bond S, oxygen, N double bond N, C triple bond C. Okay. So this is the ene reaction. So how ene reaction is taking place means the main frontier orbital interaction is occurring between the in the ene reaction is between HOMO of the ene and the LUMO of the enophile. So here the ene is the electron rich component and enophile is the electron deficient component. So the interaction will be taking place between the HOMO of the ene and the LUMO of the enophile. So this is how the reaction is taking place as we have seen in the first slide. So this is the transition state where bond breaking and bond forming are have been shown. So this is the orbital frontier orbital picture. So this is the hydrogen. It will get attached to this orbital of the LUMO, and a new carbon-carbon bond is forming between these two lobes, resulting in the formation of this final product. So here the HOMO of the ene will be reacting with the LUMO of the enophile, and hence the more electron withdrawing groups are attached to the LUMO, the energy of the LUMO will be coming down and it can interact more with the HOMO, and thereby the reaction rate will be enhanced. Okay. So some of the features of the ene reaction is that the normal carbon ene reaction, they take place at higher temperatures like 400 to 600 degrees Celsius. So if the enophile is more electron deficient, the reaction can take place at a faster rate and at a lower temperature. So I think in the lecture videos I have discussed regarding this example. So here this is the ene component and this is the enophile component. So this is an intramolecular ene reaction. So we can see the reaction is taking place at around 490 degrees Celsius, that is at a higher temperature. So if we substitute one of the hydrogen with a carbonyl group like COOMe, which is an electron withdrawing group, we can see the temperature have come down and the rate of the yield of the reaction is also getting improved. So the reaction will be taking place little faster compared to that of this case. So here this is the ene component and this is the enophile component. So the enophile LUMO have been brought down by introducing this electron withdrawing C double bond O Me, COOMe. Now, if we are substituting both these hydrogens with this electron withdrawing group like this COOMe, now the temperature, reaction temperature even come down and the rate of the reaction also increased, and it is giving this product at a much faster conversion. So you can see here the temperature have been brought down to 180 degrees Celsius by substituting this hydrogens with COOMe. That is, if we are making the enophile more electron deficient. If the enophile is becoming more electron deficient, the LUMO level will come down. So the HOMO-LUMO interaction will be more facile, and because of that, the reaction will take place at a faster rate and the reaction temperature can be lowered. So increase in electron withdrawing substituents increases electrophilicity of the enophile, which increases the rate of the reaction. Clear? Now coming to classification of this intramolecular ene reaction. So based on the difference in the tether. So this is the tethering group. Based on the difference in the tethering atoms, it can be classified into four different types. And numbering is given like The number 1 is given to allylic carbon, that is this carbon, and the number 5 is given to the carbon where hydrogen is to be transferred. So this 5 is where this hydrogen will be transferred. So the number 5 will be given to carbon where the hydrogen is transferred, and number 1 is given to the allylic carbon. So this is the allylic carbon. So number 1 is given to the allylic carbon. And when we will see the tether, it is between carbon 3 and 4. So this is the type 1 intramolecular ene reaction, which is between carbon 3 and 4. The tether is between carbon 3 and 4. Now when we consider type 2, so here if we will number, it is like 1, 2 and 1, 2 and 3, and this is the 5 where this hydrogen will be transferred. So here the tether is between carbon 2 and 4, hence it is known as type 2, which is 2,4 in reaction. Okay, and in this case type 3, the tether is between carbon 5 and carbon 1. So this hydrogen is getting transferred to this carbon 5. So this is type 3, that is 1,5 in reaction. And in this case, this is the type 4 where the tether is between. This is the tether. The tether is between carbon 3 and 5. So it will undergo in reaction like this. And it will result in the formation of this final product. So as we have seen, this XY can be C double bond C, C double bond O, C double bond N, N double bond N, O double bond O, like that. Okay. So these are the classification of intramolecular ene reaction based on difference in the tethering atoms. Based on difference in tethering carbon atoms. Thus, intramolecular ene reactions can be classified into 4 types, but type 1 is 3,4 tether, type 2 is 2,4 tether as you can see here, and type 3 is 1,5 tether, and type 4 is 3,5 tether. Now, coming to hetero-ene reactions, so this first 3 cases, here the ene is normal carbon-carbon and hetero-enophile components are involved, and in the B case, that is Konya-ene reaction and the metallo-ene reaction, so the hetero-ene component and the enophile components are involved. So coming to the first case, that is carbonyl-ene reaction or Prince reaction. So here this hydrogen is transferred into oxygen and a carbon-carbon bond is formed here. So this carbonyl-ene reaction is also known as Prince reaction. It is resulting in the formation of a homoallylic alcohol. In place of carbonyl, if we are having an imine, it is known as imino-ene reaction. Okay, so it will undergo an ene reaction like in this fashion. The hydrogen is getting transferred to nitrogen and a carbon-carbon bond is getting formed, and this double bond is shifting here, resulting in the formation of a homoallylic amine. So this is imino-ene reaction. If instead of carbonyl and imine, if a singlet oxygen is getting reacted to the ene component, we can it will result in the formation of this hydroperoxide as you can see here. So here the hydrogen is getting transferred to oxygen, a carbon oxygen bond is getting formed, and this double bond is shifting here. It will result in the formation of this allylic hydroperoxide. So this is these 3 are examples of hetero-ene reactions involving a heteroenophile. Now coming to the second category of hetero-ene reactions where a hetero-ene component is involved. So Konya-ene reaction is an example of hetero-ene reaction involving a hetero-ene. So the enol is the ene component here and the alkene is the enophile. So the hydrogen is transferred into this carbon of the enophile, like carbon carbon bond is formed here and this double bond is shifted here, resulting in the formation of this aldehyde. In the case of metalloene reaction, so the metal can be either magnesium, zinc, lithium, nickel, palladium, etc. So a allylic metal reagent is involved in the metalloene reaction along with an alkene. So the metal is getting transferred into this alkene. A carbon-carbon bond is formed here, and this is shifting here, resulting in the formation of this as the final product. So these are the different type of heteroene reactions. So this was just a brief summary of some of the important points in reaction. Now coming to question, which of the following reaction is classified as an in reaction? So four different reactions have been given and they are asking which of the following reaction, that is either A, B, C or D, which is an in reaction. So please take a couple of minutes and find the right answer. So is option A an in reaction? No, no. This is an example of Claisen rearrangement. E33 sigmatropic rearrangement, which is also known as Claisen rearrangement. So the here the electron shifting will be taking place in this fashion, resulting in the formation of this final product. So option A is an example of sigma 33 sigmatropic rearrangement, also known as Claisen rearrangement. So in option B as well, as you can see, it is a 3 2 1 1 2 3. So here also a 3 3 sigmatropic rearrangement is taking place. So the electron shift will be taking place in this fashion. So a bond will be forming here and this bond will be breaking, resulting in the formation of this cyclooctadiene. This is also an example of 3 3 sigmatropic rearrangement. Now coming to option C. What sort of pericyclic reaction is this?
Electrocyclic.
Yeah, this is an example of electrocyclic ring opening. So this is a 4n plus 2 component. So either it is not mentioned, either it is taking place by thermal or photochemical condition. It can be either H nu or delta. So it can follow conrotatory or disrotatory mode depending on H nu or delta condition. Then it will open like this and it will result in the formation of this product. So this is an example of electrocyclic ring opening reaction. So now coming to the last case. So this is an example of
Retroionization.
not retroene, it is an example of ene reaction. So this is the allylic ene component and this is the enophile. So here the reaction will be taking place in this fashion. This hydrogen will be shifting here, carbon carbon bond will be forming and it will result in the formation of this final product. So they are asking which of the following reaction is classified as an ene reaction. So among the four options, option D will be the right answer, where this is an ene reaction. In other cases, this was a 3,3 sigmatropic rearrangement. This is also an example of 3,3 sigmatropic rearrangement. Here an electrocyclic ring opening reaction is taking place, while the last case, that is option D, is an example of ene reaction. Here this is the ene component and this is the enophile component. Okay. So this is how the reaction is taking place. This hydrogen is getting shifted here, resulting in the formation of this final product. So reaction A and B are both 3,3 sigmatropic rearrangement. C, an electrocyclic reaction, particularly electrocyclic ring opening reaction, and option D is the ene reaction. Clear?
Yes, ma'am.
Okay. Now coming to question number 2. The major product formed in the following reaction is. So which reaction is this? So when you can see, this is the ene component and this is the enophile component, particularly this portion. Okay, and this is the Lewis acid which will enhance the rate of the reaction. So this is a ene reaction. So what is the final product that is forming here? So four options are being given. You can work it out and tell me the final answer.
Fourth.
Option 4 is the right answer. Now let us see how the mechanism is taking place. So here this is the enophile component and titanium isopropoxide, it is acting as a Lewis acid. It will coordinate with this electron deficient aldehyde. So it will make the aldehyde more electrophilic. Now what will happen? We are having the ene component. So the ene component will react in this fashion. A carbon-carbon bond is formed between this carbon of the double bond and this carbon of the electrophile, and this hydrogen is shifted to this oxygen and the double bond newly formed a double bond will be here. So the ene reaction will result in the formation of this as the final product. Okay, so from the above reaction we can see the first step of the reaction is titanium isopropoxide. It acts as a Lewis acid and forms complex with the oxygen atom of the more electrophilic aldehyde functional group of the substrate. So this is the enophile in our case, and among this aldehyde and ester, aldehyde is more reactive, so the Lewis acid will be coordinating with the more electron deficient or more electrophilic aldehyde component, resulting in the formation of this complex, and this complex will be reacting with our ene component. So this is the ene reaction that is taking place and it will result in the formation of this as the final product. Okay.
Yes, ma'am.
Now coming to the third question. What is the mechanism of the following reaction?
Solve it.
What?
Please solve it. Solve the question.
I did not get your. voice exactly.
Not question. I have not able to.
Actually, this is also an example of in reaction, like when we tell Prince reaction, na, where carbonyl enophile is reacting with the ene component. In reaction, particularly Prince reaction is taking place here. So the zinc bromide, it will be acting as a Lewis acid. It will coordinate with the aldehyde, and this is the ene component. So the hydrogen will be transferring here. Okay, and a carbon carbon bond will be formed between this two carbons, resulting in the formation of this product. So this is how the mechanism will be taking place. The zinc bromide will coordinate with the aldehyde, which is the enophile part, making it more electron deficient, bringing down the LUMO, so that the reaction will be taking place at a faster rate. Then the hydrogen will be abstracted by this oxygen, thus double bond will shift here, and a carbon carbon bond will be formed between these two carbons, resulting in the formation of the product. So here 1 for trans stereochemistry will be more favored. So it is giving the 1 for trans stereochemistry in the final product. Clear?
Yes, ma'am.
Okay. Now coming to the fourth question. Predict the major product of the following in reaction. So two components have been given. Please identify which is the ene part and which is the enophile part. And AlCl3 is given, which is acting as a Lewis acid. So as you can see, here the ene reaction is taking place at room temperature. We are having a Lewis acid and an electron withdrawing group in the enophile. So this is the enophile and this is the ene part. So try to work out the mechanism and find out the major product of the ene reaction. I will give a minute for solving this question. So as you can see, this is the ene component. This is the enophile component. Okay. So this reaction is taking place in a regioselective manner. Here is the largest coefficient of LUMO and here is the largest coefficient of HOMO. So a bonding will be taking place between these two carbons. So the mechanism will be like AlCl3 will be coordinating with this carbonyl group of the ester. So the beta position of the ester will be having the large LUMO coefficient, and this alkene will be having the large HOMO coefficient. So this is how the reaction is taking place. Sorry. 1 second. Then it will be tautomerizing. Okay. Okay.
Yes, ma'am.
So under Lewis acid catalysis, the reaction is highly regioselective, and the major product is obtained by a preferential formation of carbon-carbon bond with enophile beta carbon having a large LUMO coefficient. So carbon-carbon bond will be formed between these two carbons. This is having the large HOMO coefficient, and this will be having the large LUMO coefficient because of the presence of this electron withdrawing group as well as a Lewis acid which is making the like this group more electrophilic. Fine. Now coming to the
Yeah.
okay now.
Yes, ma'am. Okay.
Okay. Now coming to the next question. So this is a question based on 3,3 sigmatropic rearrangement. Predict the products in the following reaction. So here this carbon is isotopically labeled as carbon 14. Similarly this carbon also. So please try to work it out and find out which is the major product that is formed in these two reactions.
Madam, please give the answer.
What?
Ma'am, please give the answer.
Okay.
How it performs.
So this is a 3,3 sigmatropic rearrangement. Similar questions we have discussed in the previous session. So if you are drawing O, CH2, C double bond C.
Claisen reaction, Claisen rearrangement, no, ma'am.
Yeah, it is Claisen rearrangement. So this carbon is labeled as carbon 14. So if we are numbering, the numbering will be in this fashion: 3, 2, 1, 1, 2, 3. So here this reaction will be taking place in this manner. So first the intermediate will be like this. Carbonyl will be there, and here CH3 is there, and then this CH2 will be coming here. CH2, CH2, double bond C. Sorry, this will be CH. Okay, not CH2. CH double bond CH2. I will just rub and draw again. CH2, double bond CH, double bond CH2. So here now the labeled carbon is this one. Fine.
Yes, ma'am.
Sorry. This is the labeled carbon, and here we are having a CH3 as well. So this is the intermediate that will be forming. Since this cannot undergo aromatization, it will undergo another round of COP rearrangement, that is 3,3 sigmatropic rearrangement. So here it will be like 3, 2, 1, 1, 2, 3. I will number it with different color, that will be better. 3, 2, 1, 1, 2, 3. So the reaction will be taking place between, one second, I have drawn one extra bond here. Okay. So the bond will be shifting like this, resulting in the formation of final product like this, CH3 double bond O. Here a double bond will be forming, CH3, and this carbon, labeled carbon, will be coming here, CH2. So this is the 14 labeled carbon. So CH double bond CH2. Now this proton will be lost, resulting in aromatization, and we will be getting the final product like this, OH, CH3, CH3, CH2, CH double bond CH2. So here the labeled carbon will be coming at this side. So that will be the final product of A reaction. Okay. Is it clear? First,
Yes, ma'am.
first a Claisen rearrangement is taking place. It will give this as the intermediate product. So now the aromaticity here is lost. It cannot be regained as there is no proton to be lost here. So it again will undergo a COP rearrangement, resulting in the formation of this intermediate. So here a tautomerization can take place, resulting in the formation of the phenol. So the labeled carbon will be coming at this position. So we have to take care of where the labeled carbon is coming while writing the final product. Okay. Now in the second case, first step will be Claisen rearrangement, and we are not having a CH3 here. Instead, one hydrogen is present. So here itself a tautomerization will be possible, which will give the final product. So let us see what is the mechanism there. So this is the final product in A and this is the final product in B. So we can see how the reaction is taking place in case of B. O, CH2, this is labeled CH double bond CH2, and this is CH3. And we can do the numbering like 3, 2, 1, 1. One second. 2, 3. So a Claisen rearrangement is taking place in this fashion, giving final product like this, CH3. So CH2 is coming, CH double bond CH2, and this is the labeled carbon. Now a tautomerization can take place by removal of a proton here, resulting in the formation of the final product OH, CH3, CH2, CH double bond CH2 with this carbon as the labeled carbon. Clear? Any doubts?
No.
Okay. Now coming to question number 6. So the starting material, product and the reaction condition is given. Is this a conrotatory or disrotatory process?
Conrotating.
Conrotatory.
HQ.
So
Disorder.
we have to follow Woodward-Hoffmann rules. So this is an example of electrocyclic ring closure reaction. Okay. So this is what sort of system? 4n or 4n plus 2?
4n plus 2.
No, no.
4 pi plus
This is
2
4n
pi.
system. Now 4 electrons are there.
Yes, yes, yes.
Hmm? So this
Only 4 pi
4n
electrons.
system, and the
Yes, yes.
condition is H nu, right? So it will be a disrotatory process. Okay. 4n delta, 4n thermal condition is conrotatory. 4n plus 2 delta is disrotatory. Then 4n H nu is disrotatory, and 4n plus 2 H nu is conrotatory. So this is the Woodward-Hoffmann rules that we have to keep in mind. So here this is a foreign system, and the given condition is H nu. So it is undergoing a disrotatory process. So we can just ignore about the product that is given, and we will see just with the starting material and the condition whether the disrotatory process is giving this as the final product. Okay. So we are having the starting material, double bond, this is E, and this is Z. So this is the starting material and H nu condition. So 4n H nu disrotatory as per Woodward-Hoffmann rules. So disrotatory means once one is clockwise, the other one will be anti-clockwise. So if it is, this is outside, and it will be coming above the plane. This, if we move in this direction, it will be coming above the plane. So this is coming above the plane. So this is inside, and if we move it in clockwise direction, it will go below the plane. Okay, it will go below the plane, resulting in the formation of this product. So this is the product that they have given here. So it is undergoing a disrotatory process. If it is undergoing a conrotatory process, how it would have been? One second. If it is undergoing a conrotatory process, this is disrotatory. Okay, if it would have been undergoing a conrotatory process, And rotatory means both arrows will be moving in the same direction. So if it is moving in this direction, this will also be moving in the same direction. So if it is conrotatory, then how it will be? This is outside. It is moving in the anti-clockwise direction. So it will be coming above the plane. And this was inside. It is moving in the anti-clockwise direction. It will also be coming above the plane. So this is not our answer. So it is not undergoing a conrotatory process. Okay. So with the answer also we can get to know if it is disrotatory or conrotatory. But it is better to keep in mind the Woodward-Hoffmann rules. For an HNO, it will undergo a disrotatory process. Clear?
Yes, ma'am.
Okay. Now coming to the seventh question. So it is based on Jablonski diagram. Looking at the following Jablonski diagram, indicate absorption and phosphorescence corresponding to 0001 and 02 transition using the blank diagram given below. Label the transitions in your diagram. Transitions are limited to the first excited state. So the energy diagram have been given. So we are asked to indicate the absorption and phosphorescence here. So absorption corresponding to 00 will be like this. So this is the zeroth excited state. So it is not going to upper states. Then 0 to 1 it can be like this. 0 to 2 it can be like this. This is the absorption. Okay.
Yes, ma'am.
Then for phosphorescence to take place, it should come to the uh, triplet state. So for that, some other processes are there. So first here vibrational relaxation something will be taking place. Then internal conversion will take place where from the
Ma'am, please use the dark color, just like
okay,
absorption.
what okay, I will use darker color, sorry. So this is the vibrational relaxation, non-radiative process where from one vibrational state of the same electronic state to another vibrational state of the same electronic state. Vibrational relaxation. If non-radiative process is taking place from one excited state to another excited, like another electronic state, this is known as internal conversion. Okay.
Yes, ma'am.
And from this zeroth level of the S1 state coming to the ground state by radiative process, that is, it should be drawn as a straight line. Okay. Like this is known as fluorescence. This is radiative process. These vibrational relaxation and internal conversion, they are non-radiative process. So this is fluorescence. Now for phosphorescence to take place, first inter-system crossing should take place. That is from S1 to T1, the energy should be transferred. So this is inter-system crossing. ISC, inter-system crossing. So this is actually a spin forbidden process, as the from the singlet state it is going to T1 state, but because of some vibrational relaxation this is happening. And from T1 when it is coming to S1, this is known as phosphorescence. So this is also a radiative process. So it will emit light. Phosphorescence and fluorescence, these are radiative processes. And vibrational relaxation, internal conversion, intersystem crossing, they are non-radiative processes. Okay. So they have asked us to show absorption and phosphorescence. So this is the absorption line and this is the phosphorescence from T1 to S0 by radiative process, that is known as phosphorescence. So I will show the Jablonski diagram. So this is the Jablonski diagram. So this is how excitation or absorption is taking place from ground state to excited state. The by absorption of photons, the electrons will be moving to the excited state, and by this can come back to the uh, lower state by non-radiative process, which is known as internal conversion from S2 to S1. It is coming that or from S1 to S0 by non-radiative process. If it is coming, that is known as internal conversion between different vibrational levels of the same electronic state. If it is relaxing by mode of non-radiative pathway, that is known as vibrational relaxation. Then from the like S0 level, from the zero vibrational level of the S1 state, when it is coming to the S0 electronic state, that is known as fluorescence, and this is a radiative process. So this fluorescence will be taking place from the S0 level of the S1 state, means zeroth level of the S1 state. So that is according to Tasha's rule. The electron will be coming to the zeroth vibrational level of the S1 state, and from there fluorescence will be taking place. Then intersystem crossing is when electrons from the singlet state is crossing to triplet state, that is known as intersystem crossing by means of non-radiative pathway. Then phosphorescence is from the triplet state to singlet state by radiative process. If energy is released, that is known as phosphorescence. Clear? So this is the Jablonski diagram.
Yes, ma'am.
Now coming to the next question. The quantum efficiency of a photochemical reaction is defined as. So what is quantum efficiency? That is the question. The ratio of molecules decomposed in a given time to the number of quanta absorbed in the same time. So that is option A. Now coming to option B, the number of molecules decomposed in a given time. Option C, number of quanta absorbed percent time, and option D, ratio of molecules decomposed in a given time to the number of quanta emitted in the same time. So what is quantum efficiency? Out of these four options, what is the exact definition of quantum efficiency?
Ma'am, please give the answer.
So, quantum efficiency is the ratio of the molecules reacted in a given time to the number of quanta absorbed in the same time. So, option A will be the right answer. So, as we have seen in the lecture, this is the definition for quantum efficiency: the number of molecules reacting in a given time divided by the number of quanta absorbed in that time. Okay, so this is the definition for quantum yield or quantum efficiency.
Okay, ma'am.
So now if you see the options, option A is in line with the statement that is given in the lecture. So it will be the right answer. The ratio of the molecules decomposed in a given time to the number of quanta absorbed in the same time. Okay.
Okay, ma'am.
Now coming to question number 9. Which of the following principle are the principal laws of photochemistry? So in the lectures I have discussed two laws regarding two principal laws regarding
Yes.
photochemistry.
A
Option A is the right answer, that is Grotthus, Draper and Stark-Einstein law are the principal laws of photochemistry. Okay, so we can see what is those laws. So laws of photochemistry, one is the Grotthus Draper law, that is only the light that is absorbed by the molecule is effective in causing chemical changes. That is the Grotthus and Draper law. Now, coming to Einstein's Stark law, one quantum of light is absorbed by each molecule undergoing a primary photo process. So, any molecule that will be undergoing a primary photo process will be absorbing a quantum of light. So, that is the Einstein and Stark law. So, these are the principal laws of photochemistry. Okay.
yes, ma'am.
Now, coming to the next question, which of the following is an incorrect statement? So, it is based on the Jablonski diagram. Yes, it is based on the Jablonski diagram. First step in photochemistry is excited state, that is photoexcitation. B. Photochemical reactions are caused by absorption of ultraviolet light only. And option C, when a molecule or atom in the ground state, that is S0, absorbs light, one electron is excited to a higher orbital level. Option D, it is possible for the excited state S1 to undergo a spin inversion. So, which is the wrong statement among these four?
First.
First is right answer because the first absorption of light is taking place. Now, that is also
Yes, yes, ma'am. Yes.
excitation. So, option B is the right answer. That is the incorrect statement is option B. Here they are telling the photochemical reaction is happening only by absorption of UV light. No, it is wrong.
Yes, ma'am.
So photochemical reaction, they are caused by absorption of UV light which is corresponding to 100 to 400 nanometer, visible light corresponding to 400 to 750 nanometer, and some part of the infrared radiation as well, that is 750 to 2500 nanometer. Okay, so it is not photochemical reactions take place by absorption of UV visible as well as infrared radiations.
Yes, ma'am.
Okay. Now coming to the next question. So this is a um, problem that you have to solve. So here they have given a substance absorb 2 into 10 power 16 quanta or radiations per second, and 0.002 mole of it reacts in 1200 seconds. What is the quantum yield of the reaction? Quantum yield of the reaction. And here they have given the Avogadro number, that is 6.02 into 10 power 3. So for calculating the number of molecules they have given. So please try to solve and find the answer.
Eighty-one.
No, no. The correct answer is option A, that is 50. So we will solve it. Okay. So we know that Thus, quantum efficiency or quantum yield is the number of molecule reacting in a given time divided by the number of quanta absorbed in that time, right? So here first we have to calculate the number of molecule reacting in a given time. So the number of molecule reacting equal to, they have given 0.002 mole is reacting in the time of 1200 seconds. So that is 0.002, that is moles they have given. So converting it into molecule, we have to multiply it with the Avogadro number. So they have given the Avogadro number 6.02 into 10 power 23. So we can write it. So this is 2 into 10 power minus 3 into 6.02 into 10 power 23. Approximately we can write 6 into 2, 12 into 10 power 20. This is the number of molecules reacting, and the number of quanta absorbed is number of quanta absorbed equal to, in the question it is given 2 into 10 power 16 quanta per second is absorbed and the time is 1200 seconds. So we have to multiply this 2 into 10 power 16 with 1200 seconds. So 2 into 10 power 16 quanta in 1200 seconds. Okay. So 24 into 10 power 18 is the number of quanta absorbed. Now if we apply it in the equation, number of molecules reacting in a given time is 12 into 10 power 20 and the number of quanta absorbed in that time is 24 into 10 power 18. So this is zero point 0.5 into 10 power 2 which is equal to 50. Okay.
Yes, ma'am.
So we have to see each details that is given in the question. So here they have given 2 into 10 power 16 quanta per second is absorbed. So we have to multiply it with the total number of seconds. So we are calculating the total quanta like this. 24 into 10 power 18 is the quanta absorbed. And they have told like 0.002 mole is reacting. So we have to convert it into number of molecules. So for that we have to multiply it with the Avogadro number, that is 6.02 into 10 power 23. Hence we will get this number of molecules reacting. Then we have to just apply it in the equation for quantum efficiency or quantum yield. Okay, na?
Yes, ma'am.
Okay. Now coming to the next question. In dash reactions, molecules absorbing light do not themselves react but induce other molecules to react. Option A photosensitized, option B thermal, option C irreversible, option D dark. So I think in the introduction to photochemical reactions I have discussed regarding the photosensitizers. Right.
Yes, yes.
They will be absorbing light, going to excited state and giving that energy to the reactant molecules, making the reactant molecules to react, right? And they will be regenerated. So this reaction is photosensitized reaction.
Okay, ma'am.
So the molecules will be absorbing light. They do not react among the, like they do not react. Instead, they transfer that energy to other reactant molecules and induce them to react. Those molecules to react. Such reactions are known as photosensitized reactions. Okay.
Yes, ma'am.
Okay. So the reactions in which molecules absorbing light do not themselves react but induce other molecules to react are known as photosensitized reactions. The reactions which are caused by heat and in the absence of light is called thermal or dark reactions. Okay, so photosensitized reactions will be the answer for the question.
Okay, ma'am.
Now coming to the next question. Predict the stereochemistry of the product in the following reaction. Also explain the observed regioselectivity. So this is a question based on the Ene reaction. So here this ethyl aluminium dichloride is the Lewis acid.
Ma'am, please explain it.
Hello.
Ma'am, please explain it.
Okay. So we have seen that the endo transition state will be favored in if we are having a group like this substituted and in the presence of Lewis acid, we have seen that the beta position will be resulting in the formation of the carbon carbon bond. So that is explaining the regioselectivity where the low where the carbon having the largest Lumo coefficient will form the carbon carbon bond with the ene, and the endo transition state will be explaining the stereochemistry of the product. So let us see here. Under Lewis acid catalysis, the ene reaction is highly regioselective and diastereoselective. So the reaction produces two new stereo centers. As you can see here, this is also a stereo center and this is also a new stereo center that will be resulted. So the reaction produces two new stereo centers and the product stereochemistry arises from the preferred CO2 endo CO2 Me transition state. So this is having the large homo coefficient, large LUMO coefficient. So the carbon-carbon bond will be formed between these two carbons. So this is determining the regiochemistry of the product. Now if we are going to determine the stereochemistry, so we have to draw the endo transition state where the CO2 Me will be coming like towards this ene component. Okay, so if we draw the endo transition state and then if we are drawing the product, the stereochemistry will be coming in this fashion. So if we just redraw it, it can be drawn like this. Just to see the R and S conformations at these two centers. So it can be drawn like this fashion. So this is the new two stereo centers that is generated. And this is how the stereochemistry of the ene reaction is being predicted. Okay.
Yes, ma'am.
So this you have to keep in mind. This endo CO2 Me transition state that is giving the stereochemistry of the product. Now coming to the next question, question number 14. So give the mechanism of the following selenium dioxide oxidation of an alkene to an allylic alcohol. Predict the pericyclic steps involved. So this,
Any reaction.
huh?
Any reaction, ma'am.
What?
Any reaction with SeO2.
I did not get you.
Ma'am, it's any reaction. Na?
In reaction.
Yes, ma'am. In reaction.
Uh-huh. Yeah, in reaction is taking place, and one other step is the 2,3 sigmatropic rearrangement. So this is how allylic oxidation is taking place using SeO2 reagent. So let us see the step. First, this is the ene component, and SeO2 will be acting as the enophile. So this is how the ene reaction is taking place. The proton is transferred to the oxygen. A bond is formed between this selenium and carbon, and this double bond is shifting here, resulting in the formation of this component. And now here a 2-3 sigmatropic rearrangement is taking place. So we can number it like 3, 2, 1, 1, 2. A 2, 3 sigmatropic rearrangement is taking place as the arrow pushing is shown, and it will result in the formation of this product. And then upon hydrolysis or during workup, this OSC bond is cleaved and it will result in the formation of the alcohol. Clear? So the SCO2 hydroxylates an alkene at the allylic position. So the reaction involves two pericyclic steps. The first step is a hetero-ene reaction. So this enophile component is the uh, hetero part, heteroenophile, followed by a 2-3 sigmatropic rearrangement. The hetero-ene reaction involves SCO unit of the SCO2 as a heteroenophile and produces an intermediate selenic acid, which undergoes a 2-3 sigmatropic rearrangement to give the second intermediate that yields the allylic alcohol on cleavage of the SCO bond either in situ or on workup.
Yes, ma'am.
Okay, so this is the mechanism for allylic oxidation using SCO2 as a reagent.
Okay, ma'am.
Okay, now coming to the next question. So these are some questions based on um, Jablonski diagram. So, what is the process by which an excited electron transition from a vibrational level in one electronic state to another vibrational level in a lower electronic state called vibrational relaxation, internal conversion, fluorescence, or absorption? So, electron transition from vibrational level in one electronic state to another vibrational level in a lower electronic state. So, if we are drawing, this is S0, S1, S2. So from here to here, one electronic state to another vibrational level of the lower electronic state. This is what they are asking.
And vibrational relaxation?
Vibrational relaxation is taking place in the same electronic state. One vibrational level to by another vibrational level of this same electronic state, that is known as vibrational relaxation. So here from one vibrational level to another vibrational level of a lower electronic state, that is known as internal conversion. Okay.
Mm, okay.
So this is, so as you can see, this is the, this one is vibrational relaxation. This one is known as, this is from S2 to S1, that is known as internal conversion. So, vibrational relaxation is where the energy deposited by the photon into the electron is given away to other vibrational modes as kinetic energy. This relaxation occurs between vibrational levels, so generally electrons will not change from one electronic level to another through this method. So, in the same electronic level only vibrational relaxation is taking place. This relaxation occurs between vibrational levels, so generally electrons will not change from one electronic level to another through this method, and this process is also fast like absorption, which is taking place in 10 power minus 15 seconds in case of absorption. So this is also fast like it take place in 10 power minus 14 to 10 power minus 11 seconds. Now coming to Internal conversion, if vibrational energy levels strongly overlap electronic energy levels, that is, the vibrational energy levels and the electronic energy levels are very close to each other, a possibility exists that the excited electron can transition from a vibrational level in one electronic state to another vibrational level in a lower electronic state. This process is called the internal conversion. Okay, so this was our
Okay, ma'am.
excited electron can transition from a vibrational level in one electronic state to another vibrational level in a lower electronic state. This process is called internal conversion, and mechanistically it is identical to the vibrational relaxation. Like, both are non-radiative processes. So internal conversion occurs because of the overlap of vibrational and electronic energy states. Like, see, these are very close to each other now. These two electronic states are very close to each other. Like, when we are going to higher excited states, they will be coming closer to each other. So here, that is why internal conversion is taking place between vibrational level in one electronic state to another vibrational level of a lower electronic state. So it is clear na why internal conversion is the answer.
Yes, ma'am.
Okay. Now coming to the next question. Which process in the Jablonski diagram is the slowest? Fluorescence, phosphorescence, intersystem crossing, or delayed fluorescence?
Delayed fluorescence.
Delayed fluorescence is taking place in a range of microseconds, that is 10 power minus 6 seconds. Okay? So the right answer as per my view is phosphorescence.
Yes, ma'am. Possible. Yes, ma'am.
Okay? So if we are seeing, these are the time scale for different transitions. Absorption is taking place at a rate of 10 power minus 15 seconds, and it is a radiative process. Vibrational relaxation is taking place at a range of 10 power minus 14 to 10 power minus 11 seconds, same as with the internal conversion, which is also taking place at a rate of 10 power minus 4 to 10 power minus 11 seconds. And in fluorescence is taking place at a rate of 10 power minus 9 to 10 power minus 7 seconds. This is also a radiative process. These two, internal conversion, vibrational relaxation, they are not non-radiative processes. Now coming to intersystem crossing and phosphorescence, they are slower because here the transition is taking place from singlet state to triplet state, or triplet state to singlet state, which is actually uh, like not not symmetry forbidden, no? Like, the state is changing from singlet to triplet, that is forbidden according to um, rules. Spin forbidden. These are spin forbidden processes. This phosphorescence and intersystem crossing are spin forbidden processes. So because of that, compared to other other transitions, this phosphorescence and intersystem crossing are slower. And compared to in the system crossing, it is having a time scale of 10 power minus 8 to 10 power minus 3 seconds. And phosphorescence, if you see, it is having a range of 10 power minus 4 to 10 power minus 1 second. So this is the slowest process. Okay,
Okay, ma'am.
clear, no?
Okay.
Now coming to another question. What is the purpose of a Jablonski diagram? Why we are drawing a Jablonski diagram? To represent the energy levels of a molecule quantitatively, to show the possible consequences of applying photons to a molecule, to illustrate the different spin multiplicity of a molecule, to depict the vibrational energy levels of a molecule. So, what is the exact purpose of a Jablonski diagram?
Ma'am, please tell.
So it is to show the possible consequences of applying photons to a molecule. We are irradiating, we are giving photons and exciting the electrons. So whatever photophysical processes are taking place, that we are illustrating using the Jablonski diagram, right? So option B is the right answer. So coming to explanation, so the Jablonski diagram is used to show the possible consequences of applying photons from the visible spectrum of light to a molecule. It represents the transition between different eigenstates of the molecule, including absorptions, vibrational relaxation, internal conversion, fluorescence, intersystem crossing, etc. So by using straight and curved line, the diagram illustrate how electrons accept and dissipate energy from photons of different wavelength. So straight lines indicate radiative processes, and curved lines indicate non-radiative processes in the Jablonski diagram. So it provides a visual representation of the complex processes involved in the molecular absorption and emission of light. So this is the point that we have to keep in mind. So the possible consequences of applying photons from the visible spectrum of the light of the molecule. That is what Jablonski diagram is illustrating. Okay.
Okay, ma'am.
Now coming to the next question. So this was in the assignment 5 of uh, week 5 assignments of this session this year. So how will you effect the following conversion using pericyclic reaction? So they have given this is the starting material, this is the final product, and the reaction is taking place in two steps. So what will be the two steps, or what will be the mechanism of those two steps?
Ma'am, please show the mechanism.
So first, from the product that is formed, we can understand that a 3 sigmatropic rearrangement is taking place. So first, this alcohol should be converted into a vinyl ether. So here allyl portion is there, and a vinyl ether should be introduced. They should be converted into a vinyl ether. So that will be the first step, and then a 3 sigmatropic rearrangement or Claisen rearrangement is taking place, resulting in the formation of the final product. Okay, this is the mechanism. So first it is reacted with a ethyl vinyl ether in the presence of mercury 2 plus. So it will result in the formation of this ethyl vinyl ether, sorry, uh, allyl vinyl ether. So this is the starting material, this is the starting material for the 3 sigmatropic rearrangement. So since this oxygen is involved in the transition, this is also known as Claisen rearrangement. So how the mechanism is taking place? 3, 2, 1, 1, 2, 3. So a new bond will be formed between these two carbons. This bond will be shifted here, leading to the formation of an exomethylene, and here an aldehyde will be formed. And this stereochemistry is most probably because of the presence of this methyl group, beta methyl group. Okay.
Yes, ma'am.
Okay. Now coming to question number 19. How will you effect the following conversion using pericyclic reaction? So here this is the starting material and they are telling in a single step it is getting converted into this product. So what reaction is taking place here?
Clason rearrangement.
It is a sort of Claisen rearrangement, but we can think of an Ireland Claisen rearrangement in this case. So enol TMS will be involved. Okay. First, this lactone should be converted into an enol TMS, and then a 3,3 sigmatropic rearrangement will be taking place in the same pot, resulting in the formation of this product. Okay, let us see the mechanism. So, in the presence of LDA and TMS chloride at lower temperature, it will result in the formation of an enol TMS. So, the LDA, that is lithium diisopropylamide, it will be abstracting this proton and this trimethyl 1 second. It will result in the formation of this enol TMS. Okay, then this can be numbered like 3, 2, 1, 1, 2, 3. So the reaction will be taking place like this. Okay, this bond will be broken and a new bond will be formed between these two, and if we redraw that we will be getting this structure, and upon workup this OTMS ester will be converted into acid. So this is how the reaction is
Okay.
taking place. Clear?
Yes, ma'am.
So this is known as Ireland
Clason rearrangement.
Claisen rearrangement. Now coming to the last question of today's session. Suggest a mechanism for the following reaction proceeding through a pericyclic pathway.
Ma'am, form of any reaction.
No. This is an example of 3,3 sigmatropic rearrangement. So we can number it like 3, 2, 1, 1, 2, 3. Okay. Then if we redraw the intermediate, we will like if we redraw the structure that we are getting after this bond breaking and forming sequence, then we will get this as the final product. See, like this. We can number it like 3, 2, 1, 1, 2, 3. So a bond is formed between these two carbons. So we can draw it like this. This double bond is shifting here, that we can draw like this, and this bond is getting broken like this. Should be drawn like this. Okay. So that is drawn here. So if we redraw it in such a fashion, see this part is coming here, and this if we redraw, that is this part. Okay.
ओके मैम. मैडम एक चीज पूछनी थी.
Okay.
ये मैडम मेरा एक असाइनमेंट छूट गया था पिछले उसमें. 1 मिनट रह गया तब तक 12 बज गए. तो मैडम जो असाइनमेंट है मैं 6th असाइनमेंट के साथ दे सकता हूँ उसे. जो वेडनेसडे वाला
I
असाइनमेंट है उसके साथ दे सकता हूँ.
I think now you cannot upload maybe because the solutions are already been released, right? But I think some number of assignments only you have to upload, exact number I don't know. Out of 8 maybe 6 are valued or something.
Okay, ma'am. I have lost two assignment. Assignment one because my registration is late,
Okay,
and assignment fifth.
okay, okay, I think now then you have to upload all the other assignments.
Okay,
No
ma'am.
delay.
Okay,
Okay.
okay, ma'am. Thank you.
Thank you.
Thank you.
Is there any other doubts on today's session?
No, madam.
Okay, there are no further doubts. Thank you for attending.
Okay,
So I will upload the lecture in YouTube. If you are having any doubts, you can rewatch that.
okay, ma'am.
Thank you.
ओके मैम। मैम जो पुराने लेक्चर्स हैं आपके,
Hmm.
वो उसकी नोट्स मैं तो ले नहीं पाया था क्योंकि वो 5 से 6 होते हैं, तो उस वक्त वर्किंग आवर्स होता है, तो वो
Okay.
ले नहीं पाया था।
You can get it from the portal. I will share maybe. I will show
ओके
how
मैम।
to take it.
ओके, ओके मैम।
So this is the portal now. So here problem solving session one link you can see, right? So in that, this link you click problem solving session recording. So here you can see one link and that will lead to an Excel sheet. Okay.
ओके मैम।
So in this
ओके,
folder, you can see the presentations that will be uploaded, and here will be the YouTube video links.
ओके मैम। ओके, थैंक यू मैम।
Okay, thank you.